Okay, so hello and welcome back. So in this video we will discuss the properties of inverse trigonometric functions. Now there's a couple of things that we need to take into consideration here. So basically the properties of inverse trigonometric functions. So now these results are point number one is that these results are valid within the principal value branches, within the principal value branches of the corresponding inverse trigonometric functions. Inverse trigonometric functions. Right? Of the corresponding inverse trigonometric functions, and whenever they are defined. And whenever they are defined. Number two, some results may not be valid for all values of the domains of inverse trigonometric functions. Some results may not be valid for all the values of the domains of the inverse trigonometric functions. Of the inverse trigonometric functions. In fact, they will be valid only for some values of x for which the inverse trigonometric functions are defined, but we will not discuss them here because that would go beyond the scope of the text that we have here. Now, one thing that in the beginning we need to note is that basically if you say that y is equal to sine inverse of x, if y is equal to sine inverse of x, then x is equal to sine y. Then x is equal to sine y. And if x is equal to if x is equal to sine y, then y is equal to sine inverse of x, right? So which means that if I write sine of sine inverse of x, if I write the sine of sine inverse of x, that is equal to x for all x belonging to the domain of the sine inverse function. And the reason why that happens is that basically the sine inverse function takes a ratio from you, gives you an angle, then you give that angle to the sine function, it gives you a ratio, right? So now what is all of the allowed values for the domain of the sine inverse function? We said that that the domain of the sine inverse function goes from -1 to 1, which means that here x belongs to the closed interval -1, 1. And also you can say that the sine inverse of sine of x is also equal to x here being an x here being an angle, so that angle belongs to the range of sine inverse function, and the range of the sine inverse function is equal to -π/2 to π/2, right? So x belongs to -π/2 to π/2. And of course the same thing is true in the case of all the other trigonometric functions, meaning that, for example, if you go for the cos function, if I say that, for example, if I say that y is equal to the cos inverse of x, then I can say that x is equal to cos of y, and x is equal to cos of y. And also if I say that basically x is equal to cos of x, x is equal to cos of y, then I can say that basically y is equal to cos inverse of x. Right? So y is equal to the cos inverse of x, meaning that if x is equal to cos of y, x is a ratio, and this, if I give this ratio to the cos inverse function, it gives me the angle that I gave to the cos function in order to give me that ratio, right? And so on and so forth. And again over here we have I can write basically the cos of the cos inverse of x is equal to x for all x belonging to the domain of the cos inverse function, which is -1, 1, the closed interval -1, 1, and also I can say that the cos inverse of x is equal to x for all x belonging to the domain of the x function, which is, I suppose, -π to the domain of the x function. The cos function is 0 to pi. That is actually the domain to which the cos function was limited, so that based on that we could get the cos inverse function, right? So that is basically that. And you can do the same thing for all the inverse trigonometric functions and all the trigonometric functions. Now let's do a couple of some properties of inverse trigonometric functions. Let us now prove some properties of the inverse trigonometric functions. Number one, and there are basically each of these has a couple of parts. Part one is the sine inverse of 1 by x is equal to cosecant inverse of x for x is greater than or equal to 1, or x is less than or equal to -1. So the sine inverse of 1 by x is equal to the cosecant inverse of x for x is greater than or equal to 1, or x is less than or equal to 1. Okay, so now there is one thing here that you need to take into consideration, And that is basically if you try to basically to try to understand, for example, the limitations on the domain of these functions, you will get into trouble, because you will get into contradiction. And for example, I tried to do this, for example, with the first result that we have here, which is the sine inverse of 1 by x is equal to the cosecant inverse of x, and I got into some sort of contradiction, and the contradiction seems to be I was not really able to resolve the contradiction, and we basically, in the text itself, it states that in fact they will be valid only for some values of x for which the inverse trigonometric functions are defined. So these are a little bit I mean, this is just probably only for familiarizing us with all of these results. Otherwise, not that, I mean, you shouldn't actually try to understand basically the domains over here. Otherwise, you will get into some contradiction as I did. So now, number 2, or part 2 of this question, is basically the cos inverse of 1 by x. The cos inverse of 1 by x is equal to the secant inverse of x for x is greater than or equal to 1, or for x is less than or equal to 1. And part 3 of this question is the tan inverse of 1 by x is the same thing as cot inverse of x for x is greater than 0. Now, for example, if you want to prove this part over here, which is the sine inverse of 1 by x is equal to cosecant of x for these x's, what you can do is that, so to prove the sine inverse of 1 by x is equal to the cosecant inverse of inverse of x for x is greater than or equal to 1, or x is less than or equal to -1. So what you can do is that if you basically put cosecant inverse of x as y, cosecant inverse of x as y, which means that the cosecant of y is equal to x, which means that x is equal to cosecant of y. And so if I take the reciprocal of both sides of this equation, I will get 1 over x is equal to 1 over cosecant of y, which is the same thing as 1 over x is equal to sine of y. 1 over x is equal to sine of y, and that means that the sine inverse of 1 by x, is equal to y, right? And here we said that y is equal to cosecant inverse of x. So basically the sine inverse of 1 by x, I'm sorry, the sine inverse of 1 by x is equal to y, which is equal to cosecant inverse of x, and therefore that is basically, for example, this way proved. But again, you shouldn't really, I mean, since I don't really know how I'm supposed to be using these formulas, I'm not going to use them anywhere until I know what is the exact conditions on the domains and ranges of these functions. Otherwise, you might be doing something and that actually might be wrong, you know. Okay, so there are that you can basically do a similarly you can prove this the third and the second and the third part of this result, meaning that, for example, if you want to prove that the cos inverse of 1 by x is equal to secant inverse of 1 by x, so for example, to prove that the cos inverse of 1 by x is equal to secant inverse of x for x is greater than 0, you can set secant inverse of x as y, set secant inverse of x is equal to y, which means that basically x is equal to secant of y, and if I take the basically the reciprocal of this, I will get basically 1 over x is equal to 1 over secant of y, which means that 1 over x is equal to cos y, which means that y is equal to cos inverse of y by x. Y is equal to cos inverse of 1 by x. And so since y is equal to cos inverse of y by x and also y is equal to secant inverse of x, you can conclude that the secant inverse of x is equal to the cos inverse of 1 by x. And that is basically, for example, the second result that we have here. The cos inverse of 1 by x is equal to, actually this is supposed to be there is no negative here. The cos inverse of 1 by x is equal to secant inverse of x. And basically, if you want to show that, for example, the tan inverse of to prove that the tan inverse of 1 by x is equal to the cot inverse of x for x is greater than 0. What you can do is basically you can set cot inverse of x is equal to y, right? And then what that means is that basically x is equal to cot of y. X is equal to cot y, and so what that means is that then 1 over x is equal to 1 over cot of y, which means that basically 1 over x is equal to tan of y. So which means that basically then y is equal to tan inverse of 1 by x, and over here we said that y is equal to cot inverse of x and y is equal to tan inverse of 1 by x, which means that the tan inverse of 1 by x is equal to cot inverse of x. Is equal to cot inverse of x. Of course, this is all. I'm not saying anything about the domains of these functions or about the collective domain of these equations, because it's just not given here, and I'm just giving you this as as a way to get familiarized with all of this content. Otherwise, I'm not really, I mean, I don't really know how to use these in any practical situation, right? Now, that is basically number one. Number two, we have part one, which is equal to sine inverse of the sine inverse of negative x is equal to negative sine inverse of x for all x's belonging to the closed interval of -1, 1. And number two, we have the tan inverse of negative x is equal to negative tan inverse of x for all x's belonging to R. And number three, we have the cot inverse of, I'm sorry, not the cot, but the cosecant inverse of negative x is equal to negative cosecant inverse of x for the absolute value of x greater than or equal to 1, right? So this is the second thing that we need to discuss here. Okay, so basically the sine inverse of negative x is equal to that, and so on and so forth. So for example, to prove that for example, the sine inverse of negative x is equal to negative sine inverse of x for all x's belonging to the interval -1, 1. So you can do the following. Okay, so now to prove that the sine inverse of negative x is equal to negative sine x, so what you can do is that, for example, you can let sine inverse of negative x as, for example, let sine inverse of negative x be equal to y, which means that negative x is equal to sine of y, right? Which is equal to sine of y, which means that basically x is equal to negative sine y, and basically and then you can say that x is equal to sine of negative y, because basically sine of negative x is equal to negative sine x, right? So that is that, and x is equal to sine of negative y, which means that negative y is equal to sine inverse of x. And here we wanted to prove that basically the and that basically means that y is equal to negative sine inverse of x, right? Negative sine inverse of x. And what that means is that now here I have said that sine inverse of negative x is equal to y, and y is equal to negative sine inverse of x, which means that negative sine inverse of x is equal to sine inverse of negative x. So negative sine inverse of x is equal to sine inverse of negative x, and the domain that has been defined here is basically x belonging to the domain -1 to 1. That is basically that. Now you can do the same thing essentially with tan inverse and cosecant inverse. Tan inverse and cosecant inverse, and you can do that as follows. 265. And you can do that as follows, meaning that, for example, to prove that tan inverse of negative x to prove that tan inverse of negative x is equal to negative tan inverse of x as x belongs to R. So you can say that, again, you can say that basically let tan inverse of negative x, let tan inverse of negative x is equal to y, for example, which means that negative x is equal to tan inverse of which means that negative x is equal to tan of y, which means that x is equal to negative tan of y. Now we know that basically tan of negative y is equal to negative tan y, which means that I can write this as x is equal to tan of negative y, and that means that basically negative y is equal to tan inverse of x, and that means that y is equal to negative tan inverse of x. So here we are saying that y is equal to tan inverse of negative x. Here we are saying that negative tan inverse of x is equal to y, from which I can conclude that negative tan inverse of x is equal to tan inverse of negative x, right? So these are pretty simple things. Of course, x belonging to R. Pretty simple things, but again, I don't really know where we can use them. We will know more about them in the examples to come, and then there we will be able to decide, well, approximately where you can use them and where not. And as we discussed before, that the domains and the bounds on these functions are not properly defined, and I did try to figure out one of the domains of one of the first results, and I got into some sort of contradiction. And of course, I'm absolutely sure that the contradiction can be resolved if you know the exact bounds and limitations on these functions. So there is no problem with that. It's just that we have to go through this and then go through the examples, and once you get to the end of class 12, and then the whole thing will automatically take care of itself. So you don't need to worry about that. Okay, so now in order to show that the cosecant inverse of negative x is equal to negative cosecant inverse of x, to show that basically cosecant inverse of negative x is equal to negative cosecant inverse of x for all x's, the absolute value of x greater than or equal to 1. So you can say that let, for example, the cosecant inverse of negative x is equal to y, which means that basically negative x is equal to cosecant of y, which means that x is equal to negative cosecant of y. Now, you know that basically the cosecant of negative x, is equal to negative cosecant of x. That we already know, and therefore I can write x is equal to cosecant of negative y. X is equal to negative cosecant of y. And that means that basically negative y is equal to the cosecant inverse of x. Which means that y is equal to negative cosecant inverse of x. Now here we are saying that y is equal to cosecant inverse of negative x. So the cosecant inverse of negative x is equal to y, which is again equal to negative cosecant inverse of x. So, and that is for the absolute value of x greater than or equal to 1. And basically what that means is that when you say the absolute value of x is greater than or equal to 1, that means that basically either x is less than or equal to negative 1, or basically x is less than or equal to greater than or equal to positive 1. Greater than or equal to positive 1. And the reason for that is that basically the absolute value function is a function that gives you always a distance, meaning that basically the absolute value of x is equal to positive x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. So what that means is that if x is less than or equal to 0, then if x is less than 0, then the absolute value of x is equal to negative x. And if x is greater than 0 or equal to 0, then the absolute value of x is equal to x. Which means that when I say that, for example, the absolute value of 2, or the absolute value of negative 2 is equal to 2, for example, when I say that the absolute value of, when I say the absolute value of, for example, x is equal to 2, for example, what that means is that either x is equal to 2 or x is equal to negative 2, meaning that you have 0 over here 1 and 2, and negative 1 and negative 2. So that is positive 2. So that means that if I take some point on the number line, which is basically 0 on the number line, that x basically is at a distance of 2 units from that 0 mark on the number line. So if x is supposed to be at a distance of 2 units from that mark 0 on the number line, it can be either at positive 2 or it can be at negative 2. That means that this can be this can be your x, or this can be your x, and basically that is the two different possibilities of x. That means that here you can say that x is equal to plus or minus 2. Which means that basically so now if I say that the absolute value of x is equal to 2, so when I get a value 2 over here, that means that when I get so basically if I say that if my x is equal to positive 2, if x is equal to positive 2, then the absolute value of x is going to be equal to 2, because x is greater than or equal to 0. And if x is equal to negative 2, again the absolute value of x is equal to negative 2, because negative 2 is negative of negative 2. Negative of negative 2 is equal to is equal to basically positive 2, right? So the absolute value of x is equal to positive 2 here and positive 2 here, right? Now, if I say that the absolute value of x, is greater than or equal to positive 2, for example, what that means is the following. If I say that the absolute value of x is greater than or equal to 2, what that means is that basically x is some value whose distance from the 0 mark and the number line is greater than or equal to 2. Meaning that if I have the number line over here 0, basically 1, 2, 3, 4, so that is 1, 2, 3, 4 here, and that is negative 1, negative 2, negative 3, and negative 4, and here. So I'm saying that basically x is some value whose distance from the 0 mark and the number line is greater than or equal to 2. So that means that 2 is going to be my solution. Negative 2 is going to be also my solution, because negative 2 is at the distance of 2 units from the 0 mark and the number line. 2 is also at the distance of 2 units from the number line. And also all the values greater than 2, are going to basically fulfill this condition. Meaning that I'm looking for all the values of x whose distances are basically greater than or equal to 2 units from the 0 mark and the number line, which basically gives me all of these solutions. Which means that in this case I can say that, for example, x is greater than or equal to 2, or basically x is less than or equal to negative 2, right? And by the same logic, over here, when I say that x is greater than or equal to 1, that means that I can say that x is less than or equal to negative 1, or x is greater than or equal to 1. And that is basically your solution here. So that is basically this part. Now, the next part that we have here is a couple of results that have been called number 4. And the first part of that is the sine inverse of x is the sine inverse of x plus the cos inverse of x is equal to pi by 2 for all x's belonging to the interval negative 1, 1. And also the part 2 of this is the tan inverse of x plus the cot inverse of x is equal to pi by 2 for all x's belonging to R. And the part 3 of this is basically the cosecant inverse of x plus the secant inverse of x is equal to pi by 2 for the absolute value of x greater than or equal to 1, right? Now, what that means is that basically suppose that to show that basically the sine inverse of x plus the cos inverse of x is equal to pi by 2 for x's belonging to the interval to the closed interval negative 1, 1. You can say that basically let sine inverse of x, for example, be equal to y. Let sine inverse of x be equal to y, which means that basically x is equal to sine of y. X is equal to sine of y, which incidentally is equal to, if you want to basically express this in terms of pi by 2, you can use the formulas that we had before, and we said that basically if I want basically sine of y, if I want to write it in terms of some trigonometric ratio and pi by 2 and minus some the same angle over here, of course sine has to be, as we discussed before, sine has to be converted to cos, right? And let me take a look at the formulas here. We actually didn't have this in the formulas before. Let me take a look at the formulas that we had before. We had the trigonometric identities part 2, which was basically this table over here. So we didn't have pi by 2 minus x, so we have to derive all of that. So let's derive basically those formulas because we are going to need them. So if you say that, if you have basically, we know that the sine of x plus y is equal to sine x cos y plus cos x sine y, right? Plus cos x sine y. You know that sine of x minus y is equal to sine x cos y minus cos x sine y. We know that cos of x plus y is equal to cos x cos y minus sine x sine y. And we know that cos of x minus y is equal to cos x cos y plus sine x sine y. We have already done that before. Now if I set x is equal to pi by 2, and if I want to calculate, for example, the sine of pi by 2 minus x, I can use this formula here, and so I can write this as sine of, this is supposed to be x here. I'm getting a little bit faster than I used to go before, and I think that's actually necessary. So the sine of pi by 2 cos of x and minus cos of pi by 2 sine x. Now basically the sine of pi by 2 is equal to 1, so that is cos x, and cos of pi by 2 is equal to 0, so this whole thing goes to 0. So that means that sine of pi by 2 minus x is equal to cos x. Now if I say that basically what is the cos of pi by 2 minus x? The cos of pi by 2 minus x is equal to, I can use this formula here and write this as cos of pi by 2 cos x plus sine pi by 2 sine x, right? And cos of pi by 2 is equal to 0, so this whole thing becomes 0. Sine pi by 2 is equal to 1, so this is equal to sine x. So cos of pi by 2 minus x is equal to sine x. Now, what is, based on this, you can calculate tan of pi by 2 minus x, which is equal to sine of pi by 2 minus x over the cos of pi by 2 minus x, which is equal to cos x over sine x, which is equal to cot x. That means that tan of pi by 2 minus x is equal to cot x. Moreover, you can say that the cot of pi by 2 minus x is equal to the cos of pi by 2 minus x over the sine of pi by 2 minus x, which is equal to the cos of pi by 2 minus x is equal to sine x. The sine of pi by 2 minus x is equal to cos x, which is equal to tan x. Which means that the cot of pi by 2 minus x is equal to tan x. Moreover, what you have here is that the secant of pi by 2 minus x is equal to 1 over cos of pi by 2 minus x, which is equal to cos of pi by 2 minus x is equal to sine x. So 1 over sine x, which is equal to cosecant x. And the cosecant of pi by 2 minus x is equal to 1 over sine of pi by 2 minus x. Sine of pi by 2 minus x is equal to cos x, so that's 1 over cos x, which is equal to secant x. So that means that the cosecant of pi by 2 minus x is equal to secant x. Secant x. Now if I were to put all of these together, we said that basically okay, so we said that over here, so we said that basically sine of pi by 2 minus x is equal to cos x. The cos of pi by 2 minus x is equal to, how do I erase things here? Pi by 2 minus x is equal to cos of pi by 2 minus x is equal to sine x. And we have the tan of pi by 2 minus x. The tan of pi by 2 minus x is equal to cot x. And we have the cot of pi by 2 minus x. Cot of pi by 2 minus x is equal to tan x. And also we had the secant of, we had basically cot, the secant of pi by 2 minus x. The secant of pi by 2 minus x is equal to cosecant x. And also the cosecant of pi by 2 minus x is equal to secant x. So as you can see, when you have pi by 2, as we discussed before, sine is turned into cos, cos to sine, tan to cot, cot to tan, secant to cosecant, cosecant to secant. And when you have pi by 2 minus x, all of the trigonometric ratios are positive. And now what I'm going to do is that I'm going to just simply make a screenshot here and go back to what we were doing before. So I'm going to write this as trigonometric just part 8, for example. And basically okay. Now, so basically going back to what we were doing here, so we said that basically we wanted to show that the sine inverse of x plus the cos inverse of x is equal to pi by 2 for all x's belonging to this interval. And we said that we could let sine inverse of x be equal to y, which means that x is equal to sine of y. Now sine of y, you can write it as basically cos of pi by 2 minus y, because we said that the cos of pi by 2 minus x is equal to sine x. We already showed this in the results that we did before. So which means that basically sine of y, I can write it as cos of pi by 2 minus y. That is equal to x. So if x is equal to the cos inverse of cos inverse of x, so I can write here the cos inverse of x is equal to pi by 2 minus y, right? And pi by 2 minus y, which is equal to, and y is equal to sine inverse of x. So I can write the cos inverse of x is equal to pi by 2 minus y, which is equal to sine inverse of x. Which means that basically if I take the sine inverse to the other side, I will get the sine inverse of x plus the cos inverse of x is equal to pi by 2. And in the same way we can prove basically all the other results that we have here, meaning that, for example, the second result that we had here was for example the second result that we wanted to prove here was, for example, the tan inverse of x was the tan inverse of x plus the cot inverse of x plus the cot inverse of x is equal to pi by 2 for all x's belonging to R. So I can take, for example, the tan inverse of x as y. Let tan inverse of x be equal to y, which means that basically x is equal to tan of y. And since I need pi by 2 here, I'm going to use the same results that we had here. I'm going to write, so basically you can see that tan of x is equal to cot of pi by 2 minus x, right? So tan of x is equal to cot of, we know that tan of x is equal to cot of pi by 2 minus x. Which means that I can write x is equal to cot of basically pi by 2 minus y, right? And that basically means that pi by 2 minus y is equal to cot inverse of x. Pi by 2 minus y is equal to cot inverse of x. And y is equal to tan inverse of x, so I can write pi by 2 minus tan inverse of x. Tan inverse of x is equal to cot inverse of x. Which means that if I take tan inverse to the other side, I will get tan inverse of x plus cot inverse of x is equal to pi by 2. And that is the second result that we wanted to prove here. The third result that we had here was the cosecant inverse of x. The cosecant inverse of x plus the secant inverse of x is equal to pi by 2 for the absolute value of x greater than or equal to 1, right? So let's see what that is. Okay, so now to prove that the cosecant inverse of x plus secant inverse of x is equal to pi by 2, you can say that, for example, let cosecant inverse of x is equal to y, which implies that basically x is equal to cosecant of x is equal to cosecant of y, and cosecant of y, if I were to, I can write it as based on what we said here, is equal to basically, based on what we said here, is equal to secant of pi by 2 minus x. So you can say that basically the secant of, you can say that the secant of pi by 2 minus x is equal to cosecant of x. And basically, having that in mind, I can write basically x is equal to, instead of cosecant of y, I'm going to write secant of basically pi by 2 minus y. And so what that means is that pi by 2 minus y is equal to secant inverse of x. And what that means is that take y to the other side, secant inverse to the other side. I can say that basically y is equal to pi by 2, y is equal to pi by 2 minus secant inverse of x. Now y is equal to pi by 2 minus secant inverse of x, and it's also equal to cosecant inverse of x. So I can write cosecant inverse of x is equal to pi by 2 minus secant inverse of x, which means that take secant inverse to the other side, secant inverse of x plus cosecant inverse of x is equal to pi by 2, right? So that is basically part 4 of these results. There is a couple more parts that we will discuss in the next video. So I'll see you in the next video, and thank you.